Welcome to lecture 29. In the last few classes, we have been studying the shear strength and stress strain behavior of soil and stress, strain, pore pressure response using traction testing, wherein a sample is confined laterally and we study the conditions under three types of tests: drained, consolidated undrained, and undrained condition, depending on whether you allow drainage or close the wall. The most important thing you should know is when you look at stress strain behavior, loose sands and soft clays have large deformations before they reach failure. And if you allow drainage, the volume changes, volume decreases. This is volume decrease. Whereas if you have, this is for loose sands or normally consolidated soils. Whereas if you have dense sands or over consolidated clays, what you find is a maximum value and a ultimate value or residual, we call it. This is also called residual strength. And the most interesting thing would be if you allow volume change, this will be volume increase. And again you are plotting with sigma 1, the volume increases. So for different intermediate states, the behavior would be between these two. If you do undrained test, the exact opposite happens. This is in the case of a drain test. If I do undrained test, what you find here is a positive pore pressure, whereas here, if in case of dense soils, over consolidated soils, saturated ones, you will find the pore pressure can be negative. The soil has a tendency to expand, but since we close the wall, no water can enter, so whatever water is inside will be under a tension or negative pore pressure. You may call it suction, but basically it is negative pore pressure, because of which it will have relatively high strength. The other important aspect is, in nature, soils can be very, very soft. So we have what we call as a soft soils. They are all along the coast. If I have the coast of Andhra Pradesh here, you will see that right from Nellore, Krishnapatnam up to Srikakulam, we have soft soils. There can be clay silts, silty clays, or predominantly clays. We call them as marine clays because they have been deposited in the sea by all the rivers that are reaching the sea. It could be Krishna Godavari Delta, it could be Vamsadhara, it could be Pennar, whatever it is. So you find that all our pores are affected by these soils. If the soil is soft, you cannot get easily a sample. Remember, to do triaxial testing, you need a sample which is 35 millimeters in dia and about 75 millimeters high. To take it off the ground from some depth here, it's not easy. The soil may be so soft it may try to fall down. So we had to determine the strength in the ground itself. And in the lab, if you want to do, we don't take it out of the tube, but try to do inside the tube, sampling tube itself. So to determine the strength of soft soils, we have what is called as a vane shear test, which was developed some time back and is a very simple, powerful technique. What we have is a rod to which we connect two blades. This is one set of blades, this is another set of blades, and at the top you have a handle, so that I can rotate the handle and we push this inside to the ground. If you look at the plan, you will see there is a rod, you have a vane, two sets of blades. So if you can imagine, to this rod, you have one set of blades here, another set of blades. So when I twist this, you will find that the soil within the blades gets sheared. So what we do is, we push it into the ground. Let us say the ground level is here, and we make a hole, say 2.5 meters. I push the vane here and try to rotate it. So it is simply like you would have seen one of these car jacks at the top. We hold it and then rotate it. So you are applying a torque. This is a torque which is applied to the rod. When you apply the torque to the rod, these blades which are inside the ground, they try to move, and then you will get a cylinder of soil being sheared. So when you look at this, what you will find is you have the rod here and the vanes. So you will get the soil being sheared at the top and bottom and all along. So when I am shearing it, the soil develops shear resistance, and these are all soft clays, and we do the test in a very short time, which means probably each test is finished in about 5 to 10 minutes. The vane is given at least 1 or 2 rotations per minute, so you are turning it fairly fast. And then you measure how much torque I need to twist it and get the maximum strength. So if I now know T max is the torque required to rotate the vanes. So that gives me the maximum torque, which depends on the strength. How do I find out? You agree that this is height h and the diameter is, let's say, d, small d, let's say we take it. So you find that when you rotate this, if this is the cylinder, you will get shear resistance being mobilized along the cylindrical surface. And you are finding out torque, which is the moment about the center. So whatever is the torque resistance moment about the vertical axis, plus the flat surface here also gets sheared at the top and bottom. So what you will find is the torque is due to resistance mobilized along the cylindrical surface, the soil contained within these blades. So this is the diameter d, and over the height of the vane, which is equal to h. So that will be the cylinder we have, and that cylinder moves inside the soil. So we will get this T is equal to the torque, T max, you can derive, is equal to 4. I'll tell you what this parameter beta is a parameter. Cu pi d square h, where d is the diameter and h is the height of the vane. Diameter can be around 15 centimeters, the height can be about 30 centimeters, or it can be 10 centimeters and 20 centimeters. Usually height is twice the diameter. So you will have a large cylinder which is rotating. So the first part is the torque mobilized due to strength on the cylindrical surface, and the second part is the strength mobilized on the top and bottom surfaces of the cylinder, because you are pushing the vane into the ground, so the top and the bottom of the vane are within the soil. This beta is a parameter that tells us, suppose this is the rod and the vanes are being rotated. So if the strength is fully mobilized, this is R as you go, radial distance from the center. If the strength is fully mobilized, then beta is equal to 2/3. Whereas you say, no, the strength cannot be mobilized at the center, and you will say the strength is fully mobilized, well, linearly mobilized, then beta is equal to 0.5. Whereas you say, no, it may be parabolic, it could be something like this, then beta is equal to 0.6. But usually we take this as our simple assumption. So you will get beta is equal to 2/3, means it will be d cubed by 6. So T max is equal to Cu pi d square h by 2 plus d cubed by 6, assuming the strength is mobilized all along uniformly. So the soil goes into an undrained state. Please remember, we are using Cu, which means it is called undrained cohesion. So if I know torque, maximum torque I require, or in order to rotate the vane inside the ground by 1 or 2 revolutions, or even half a revolution, Cu into pi, square of the diameter into the height of the vane by 2 plus diameter cubed by 6. So now you can easily calculate Cu, which is equal to, so Cu is equal to T max, maximum torque, by pi d square h by 2 plus beta into d cubed by 4. And you can apply whatever beta you think is appropriate to the condition. So here is a very simple technique. All that you do is push the rod with the vane, rotate it, and find out the torque, and you will get the undrained strength. We do something else after that. After you get obtaining T max, the maximum torque, rotate the vane about 5 to 10 times. So what you do is, again push it in, and then using the torque thing, wrench, we keep on doing this way, and you will find you are disturbing the soil, and you get what is called as remolded strength. And you try to find out T remolded. We have completely churned the soil, so it has become highly disturbed, and if it is highly disturbed, you get remolded strength, which is much smaller. So once you get the T remolded, I can get Cu disturbed or remolded, say Cu remolded is equal to T remolded by pi d square h by 2 plus, let's say, beta into d cubed by 4. Note two things you find. First time when I give a slow rotation for maybe half a rotation or one rotation, I get a very high torque. So if I now look at it, suppose I plot theta versus t, I get a maximum value, T max. If I increase theta, it will reduce, and you will get T remolded. That's same thing as our triaxial test, wherein you get the maximum strength and the ultimate or yield strength or highly disturbed strength. So from field, we can determine both the maximum torque and the remolded torque, from which we will get Cu undrained cohesion, and the remolded value. Why do we need this? Because you can now define a new term called sensitivity. Symbol is St. We say Cu, if you want to say undisturbed, divided by Cu remolded. If you can do the test without disturbing the soil, you will get undisturbed strength, which is relatively high. And if you find out the undrained strength after remolding the soil, you get remolded undrained strength. And that ratio is called sensitivity. And this value can vary from 1 to even 100 or more. Imagine if the sensitivity is 100, it means if you disturb the soil the strength reduces to 1/100th. Fortunately, in our state and in India, we don't have two sensitive soils. For example, if you try to test from Visakhapatnam clays, Kakinada, Srikakulam, etc., sensitivity is only of the order of 2 to maybe 6. So if you try to disturb the soil, the strength may reduce because undrained remolded strength will be undisturbed strength by, which means when you do construction in these soils, you have to try to maintain as close to undisturbed state as possible. The moment you disturb it, the soil will lose strength. Here we have a table. If the sensitivity is 1 to 2, we use the term slightly sensitive, 2 to 4 medium sensitive, 4 to 8 is very sensitive. And the moment it goes beyond that, these are called quick clays. And then if it is, this is called slightly quick. Imagine 16 to 32 is medium quick, 32 to 64 is very quick, and anything more than that is called extra very quick clays. Why do we call it quick clays? The problem with them is the moment you touch them, even a slight disturbance makes them collapse and it starts flowing like a liquid. Whereas fortunately for us, they reduce only by a factor of 2, 3, 4. Maybe in the west coast near Bombay, Cochin, there may be a sensitivity to the order of 4 to 6. I'll give a simple example. I want to drive a pile in Visakhapatnam port, and if I now try to drive a solid tube, the moment the soil is disturbed here, the soil here becomes very, very soft and it cannot take any more load. So we never do that kind of thing. We recommend a board pile so that the soil gets least disturbed. So I drive a small thin tube, remove the soil rather than pushing it laterally. So when you have soft clays, you have to be extra careful not to disturb it, so that if it loses strength, you can't construct anything on top. Or the cost of construction goes up, the whole thing starts flowing in. There was an excavation made in one of the sites, and because of the disturbance, the whole soil flowed into the excavation, and we had a lot of problem because it was not taken care of properly. So sensitive soils are very, very difficult to deal with. The reason why they are sensitive is because they have been deposited under the sea, which means under sodium chloride conditions, and then the water, the whole thing got leached, and instead of a chemical, now you have water. And because of that, the particles become very, very weak at the joints. If you disturb it, the interparticle forces get lost and the soil collapses. Another advantage with vein test is that I can determine the strength at different depths. So if I now plot Cu as a function of depth, what you find is initially it may decrease, but generally the strength increases with depth. The reason is soil is the same. It's a homogeneous deposit. So materially it's the same. But if I look at a point here and here, depth is Z1, Z2, you agree that the total stress sigma 1 is gamma into Z1, sigma 2 is gamma into Z2, and then sigma 1 prime is equal to gamma Z1 minus gamma W into, let's say, water table is close to the ground level, and sigma 2 prime is again gamma Z2 minus gamma W Z2. Sigma 2 prime is greater than sigma 1 prime. The effective stress as you go deeper is increasing. If the effective stress is more, you have seen in your consolidated undrained test, you get the highest strength. So what we find is Cu by sigma prime is a constant. It increases linearly, and this constant is given by Skempton way back in 1950s. We may have to modify for our own soils, plus 0.037 into plasticity index. The more plastic the soil, if Pi is more, the increase is more. Usually I would say this is approximately around 0.23 to 0.25. The undrained strength is about quarter of the effective vertical stress at that depth. The second thing you should know is to correct for the vein strength. How is the strength determined in a triaxial test? We have sigma 3 and we have a deviatoric stress. Whereas in the vein, you are applying a torque and shearing in a different way. So if I want to find out Cu from triaxial and you have Cu from vein, they may not be same because there are two different types of tests, and so we have what is called as a correction factor. So if you determine Cu from vein, Cu that you should add out for design, which is more or less closer to triaxial or whatever call, let's say the embankments, etc., lambda times Cu vein. This undrained strength determined from vein test has to be multiplied with the parameter lambda. And this lambda again is a function of the plasticity index minus. So all that you have to do is determine undrained strength from vein test, multiply with the factor. This factor lambda is a function of plasticity index. And then you will get the appropriate one to use for our design. Could be a foundation, could be pile, it could be an embankment, a liquid storage tank, whatever it is. Do not use directly the undrained strength you determine from vein. Use a factor to get the corrected value. So please remember, this is absolutely necessary. So what we have found out from this is that soft soils can be easily tested to determine the strength, and this tool is used to determine strength at various depths. You make a borehole, push the vein, then conduct the test, then take the vein out, extend the borehole, repeat the whole process. Two other things are very important. One is we said sensitive soils. They lose strength due to disturbance. So the strength decreases. There is a phenomenon that occurs which is opposite. We call it a thixotropy. I don't know whether you have noticed it. When your mother, sisters, whoever it is, they make curd, initially to the milk you add a bit of todu, and after some time you find that the whole thing becomes semi-solid and sometimes fairly hard, and that is nothing but thixotropy. The same milk with the culture becomes harder. So thixotropy is gain in strength with time. So for example, I'm plotting Cu versus time. In the undisturbed state, the strength is high, but the moment you disturb it, it may become smaller, then it may gain. Again, if you disturb, it will come down and keeps on changing. And this gain in strength, I think it should be the other way. So you find that given time, some soils can regain their strength. Then these are called fully recoverable strength. Whereas some soils, it cannot be fully recovered. So I have strength versus time. Initially, let's say, strength is high, come down. This is partial recovery. So you have to be also, if necessary, take care of the gain in strength over a period of time. It can be 6 months, it can be 1 year. So if your project can wait, after we disturb the soil and wait, maybe the soil can gain 50%, 80% or 90% of the strength. So this is absolutely necessary, interesting to study, another unique feature of soft soils. Sometimes you also find in sands, if you vibrate, they may lose their strength, but over a period of time, they gain in strength. The third most important phenomenon with respect to strength is a particular process called liquefaction. This happens in sands. You might have seen in some of these pictures of Fuji earthquake or any of the ones that were in Japan, etc., wherein a ground which looks solid, then an earthquake comes. Then you have the energy, like the Fuji earthquake of 2001, magnitude of the earthquake is at the order of around 7. It's a fairly high intensity one, and if you have loose saturated sands, so which means the groundwater table is somewhere high, it's a loose sand, which means the relative density is less than about 45 to 50%, usually 25 to say 35%. You call it as a loose sand, 15, 25, 30, 35, you call it. Suddenly under earthquake, the whole thing becomes a liquid. And anything you build on top, because it's a liquid, it will either try to sink, it will try to rotate, it will fall, collapse, all kinds of things can happen, which in fact happen because the soil below has become a liquid. So the process under which a good solid ground which looks normal under ordinary conditions during an earthquake becomes a liquid, and the process is called liquefaction. Why does it happen? This happens only in case of sands. Even though the permeability is high, earthquakes occur over a very short period of time. Duration of earthquake is usually only of the order of 20 seconds. Now 20 seconds is not enough for the pore water pressure to dissipate. So I have a sand which is subjected to shaking, and it is saturated. So once you apply any shaking, the pore pressure increases. And once pore pressure increases, please remember the total stress is the same. Sigma is gamma into Z. So the total stress remaining same, if U is increasing, sigma prime, the effective stress decreases. And if effective stress becomes 0, that means the pore pressure generated inside is equal to the total stress, the effective stress becomes 0. Once it is 0, the whole thing collapses. So to do this, what we do is a cyclic triaxial test in which you apply on the sample this vertical load number of times. You apply, remove, it's a dynamic load till the soil gets liquefied. Count how many cycles you have to apply, and from there we try to determine whether the soil is likely to liquefy during a 20-second duration earthquake or longer. So cyclic triaxial test is necessary if you want to study liquefaction potential of most soils. Okay, so this is how we normally do the liquefaction. In the field, of course, we have separate tests. We can do a standard penetration test, a cone penetration test, etc., in order to determine the liquefaction potential. Those are in situ tests. The second thing that can happen is the liquefaction can lead to total loss of strength, and it behaves like a liquid, or we call it as cyclic mobility when the strength is partial loss only. In this case, strength may reduce by 50 to 70%. Once it becomes so soft, say strain versus stress, Original strength is here. Now it becomes and very large strains, which is also bad. The only thing is the structure may not collapse, whereas in this case it can collapse fully. Another very interesting thing you will find is suddenly you will find this saturated soil coming out like a fountain, and you will get these volcanic craters kind of thing here. The sand which is below is under such a liquefied state with high pore pressure, it comes like a jet and deposits on the surface. So you will find suddenly the sand which is below here comes out during an earthquake and gets deposited all around on the ground surface. I would like you to look into the internet. I'll try to show some pictures too, wherein you find that the sand which is below ground level has come out now. So when you study strength, these are the various special exclusive characteristics of the soil. Soft clays with strength increasing with depth. Please remember, soft clays, strength increases with depth. Then sensitivity, strength loss due to disturbance, loss of strength due to disturbance. And liquefaction is also something like that. The only thing is this disturbance is caused by nature itself and not by human activity. A major earthquake hits the place, and then that's enough to cause the liquefaction, because the energy released during an earthquake is very, very high. So please remember, these are the. Then there's a positive side of it. If you have time, soil gains its strength. Gain in strength is called thixotropy. So we need to study sensitivity, the liquefaction potential. But let me tell you, for smaller earthquakes of magnitude 6 or less, liquefaction is very unlikely. And particularly in this region, we are in zone 2 of the earthquake magnitude according to the Indian standard, where the maximum earthquake that can occur in coastal Andhra or say Vijayawada, etc., is only of the order of 4, 4.5, maximum 5. So we have very little chance of getting liquefaction. But if you do end up working in a area like Gujarat, in the Ganges Delta, Brahmaputra Valley, you may find that the liquefaction can be a serious problem. So this tries to complete our study of strength and stress strain behavior of the soil.